Problem 11.87. So there's a bar that we're trying to measure the mass of. So capital M is the mass. This bar is 4 meters long, and we're told that it has holes and stuff in it, so its center of mass is not in the middle. In fact, the center of mass of the bar, we're told, is 1.88 meters from its left edge. So we then are told that we place the bar, when we determined this by placing it on a knife edge pivot, and then we're told that we place the bar slightly further to the right and then suspend a mass from one end and then another mass that we move along and measure where the center of mass of the whole system moves to. And we have this table here, and there are a few things we need to do. So the first thing is to draw a free body diagram, and this will help illustrate what it is exactly that we're talking about. So we have our bar. Mass 1 is suspended 0.2 meters from the left-hand side. The knife edge pivot is here, 1.5 meters from the left-hand side. We'll call the normal force it exerts Fp. The center of mass of the bar is over here at mg. Oh, and this is 1.5 meters from, oh, I already said that, I think. But it's 1.5 meters from the left-hand side. This is 1.88 meters. And then this is the second mass, and the distance from the left-hand side to the second mass is x, and we pick different masses for this and find out where we have to position it to balance the bar on the pivot. So here's our free body diagram. Next, we want to plot, or not plot, sorry. We want to use the equilibrium condition to find our x here as a function of the second mass. So this weight over here has a mass of 2 kilograms. And we're using the axis, for the axis we're using the pivot. This acts 1.3 meters from the pivot. We have the mass of the bar and its weight and the acceleration of gravity to make this its weight. This is 1.88 meters. Wait, no. It's 1.88 meters from the left-hand side. So it's 0.38 meters from the pivot. And this will have second mass here subtracted from it. And then x minus 1.5 meters because x is from the left-hand side, but we're measuring from the pivot. This all needs to equal 0. And so we just solve this for x as a function of m2. Well, I mean, it'll be a function of all these things, but the rest of them are constant. And we get 1 over m2 times, actually this is, I'm going to need to make a little more room for this. X is going to be, 1 over m2 times 2 kilograms times 1.3 meters minus m times 0.38 meters, m plus 1.5 meters. So now we want to plot x as a function of 1 over m2 this is in inverse kilograms, this is in meters, so 0.2 inverse kilograms, this is 2 meters, and then at 1 inverse kilogram, it's 3.5 meters. And here would be our best fit line. Obviously, you should plot, in your plot, all of the values that are given, but this is just a sketch of what it would end up looking like. And then, however you like to do these things, you make a best fit line. And from that, you will find that m, the mass of the bar, is 1.59 kilograms. This is part C. So now, from doing the best fit line, we also find that the y-intercept, so this right here, is at 1.5 meters. And so this makes sense because as 1 over m goes to 0, or 1 over m2 to be specific goes to 0, this is the same as saying that m2 goes to infinity. And so as this becomes larger than all of the other masses involved, you're going to have to, and recall this is the location of the knife edge pivot. And so you're going to have to, basically put this giant mass as close as possible to the pivot as it gets larger and larger, so that the center of mass of the system will be over the pivot. So this makes sense because as this gets bigger, it has to get closer to the pivot so that the moment arm of the torque that it produces is smaller because the force is increasing.